Hello everyone, and thank you for joining this webinar on coastal processes and sediment transport. My name is Meven Wiban. I'm a coastal engineer at DHI Australia, and today I'm going to give you some background on coastal processes that are important for sediment transport. Flow and sediment transport in the coastal zone are very important in relation to several engineering topics such as sedimentation, erosion around structures, backfilling of dredge channel, changes in the nearshore morphology, and longshore and cross-shore transport. So what we're going to do today is look at the coastal processes that are important for sediment transport, and then detail longshore and cross-shore sediment transport. And in the end, we will look at how the human project can have interaction with the shoreline evolution. Here is an overview of different activities and different processes that are occurring on the coast. We can see that there are natural processes such as waves and currents and rivers supplying sediments in the coast. There are also human activities like agriculture and industrial development. And there are also town and industries. We know that nowadays there is an increased pressure on the coast. More and more people want to live close to the coast. There are more and more habitation on the coast. There are also larger harbors due to larger ship traffic. So all this leads to an increased pressure on the coast. And shores are active due to the impact of waves and currents and storms on the geology. And as we will see later, the coastal landscapes are also impacted by the developments, which may cause conflicts with the nature. It is important to keep in mind that all these coastal impacts are very often interrelated. And to understand all these processes, we are lucky because today we have a better understanding of the physical processes themselves. We also have access to much more field measurements, and we also have numerical models that are enabled to help us predicting the shoreline evolution. So what are we up against on the coast? Well, basically there are very strong natural forces that are hitting the coast, such as waves and currents. And usually the shoreline will respond with an active morphology. As a consequence of this, we have typical problems such as coastal flooding and coastal erosion that can be very problematic when there are activities or people that are located on the coast. So what causes changes to the coastlines? Well, first, it's important to keep in mind that the coastlines have an historical evolution, even without the intervention of humans. Generally, we can say that the appearance of the beaches is determined by the hydrographic conditions of the site and the geology of the site. Any interference will cause a reaction in the form of a shoreline response. And this response can be more or less pronounced and more or less quick. Therefore, it's important to understand the physical processes that are responsible for this evolution in order to successfully plan the design and the developments of the nearshore zone. In the end, all this is related to sediment transport. Waves and currents are the driving forces for sediment transport. We often distinguish two types of sediment transport: the longshore sediment transport, which runs parallel to the shoreline, and the cross-shore sediment transport, which is perpendicular to the shoreline. The understanding of the coastal processes makes possible to describe and quantify the sediment transport quantities, and therefore quantify the impacts of different developments, and also develop solutions to avoid serious problems along the coast. This is a schematic way of showing what we are going to look at today. And it shows different components of sediment transport. So we have currents and waves, which are the forcing. And all this together will lead to the estimation of sediment transport quantities. And depending on the sediment transport quantities, we will have a potential morphological change. This morphological change will have a direct impact on the forcing itself, which will be different from the previous state. First, let's have a look at the waves. Waves are very central when we're dealing with sediment transport. And here you can see, for instance, an example of a wave field and the interaction with a coastal structure. It can be very difficult to describe. So let's have a look at the different processes that can affect the waves. Typically, we distinguish different types of waves based on their period. We first have the wind waves that are generated by a local wind and which have a period of, let's say, below 8 seconds. Another main type of wave is the swell waves, which are typically generated by distant wind and which have a period which is larger than 8 seconds. And finally, infragravity waves, which are long-bound waves released due to wave breaking in the nearshore zone. And these waves have typically a period of minutes, in the order of minutes. So let's have a look at the life cycle of a wave. First, the wind disturbs the water surface, and that's how the waves are generated. Then the waves can continue to grow if the wind continues. And then the waves can propagate with or without the influence of the wind until the waves reach the shore, where they will dissipate and potentially break on the shore and also generate infragravity waves. As we've seen before, the waves are generated by the wind in deeper water, and then they will propagate towards the shore with a certain speed. And depending on the bathymetry or whether there are structures on their way to the shore, they will be affected. For instance, here on this plot, we can see that there is a breakwater which is located in the middle of the coast. And when the wavefront will reach this structure, it can potentially be reflected by the structure, which will conduct in having a wavefront in a different direction. There is also refraction occurring and shoaling and breaking, but we will have a look at that in a bit more details now. So let's have a look at the refraction. Refraction is a change in direction of a wave due to the change of its speed when it reaches a shallow area. When the wave reaches a shallow area, the part of the wavefront which is in the shallow area slows down, whereas the part of the wavefront which remains in the deeper area keeps its original speed. And this will typically lead to a bending of the wavefront. Another important process is diffraction. Diffraction occurs when waves encounter a surface-piercing obstacle, such as breakwater, a natural headland, or even around an island. The diffraction is the spreading of wave energy into areas which are sheltered by the structure. The energy is transferred laterally, which leads to having waves even in the lee zone of the structure. Usually, wave heights are reduced as the wave energy is distributed over a longer wavefront. When waves propagate in the shallow area, we've seen that they may change direction due to the bottom friction. Another thing that occurs is that the waves slow down, and the kinetic energy of the waves are transformed into potential energy. And this leads to a slower but higher wave. This process is known as shoaling. When the waves get higher and higher and slower, it continues until the waves become unstable and breaks. So as we've seen, there are a lot of processes that can affect the waves. In order to be able to work with the waves, we would like to have a description of the waves that is easy to handle and that is easy to analyze, for instance, statistically, in order to have a feeling of the wave conditions at a specific site. For this, we use typical wave parameters such as the significant wave height, the mean wave period or the peak wave period, and the mean wave direction. These parameters are usually calculated based on the wave energy spectrum, which describes the wave energy distribution on different wave frequencies and wave directions. So this is an example of a multi-peaked wave climate. On the bottom right, we can recognize Australia, where significant wave height is displayed. And on the left, we can have a look at it's a zoom on the Brisbane area. And in the bottom left, we have a representation of the wave energy spectra, depending on the direction and the frequency. What we see here is that when there are red color, there is a peak of energy. And we can see that at some specific times, we have peaks of energies coming from different directions. It's important to have in mind that the integrated parameters are calculated for a specific spectra, but this spectra is not necessarily as uniform as it can be seen in the parameters. So now we've looked at the wave. Let's have a look at another important parameter for the sediment transport, which is coastal currents. The currents can be divided into ocean currents and nearshore currents, but in our case, it's only nearshore currents that have an influence on the coastal processes. Currents in the coastal zone are typically forced by different components, such as ocean currents, which are large-scale circulations due to density gradients in temperature and salinity. There is also the tide that has a significant importance for the currents. Atmospheric conditions will lead to current modifications as well, and in the end, the breaking waves that will generate very strong currents, which is very important for the sediment transport. So basically, when the wave break, there is a gradient in force that is induced on the coast. And this gradient is reflected in a gradient in the radiation stresses. If we look at the two different components, the cross-shore components is balanced by a slope of the mean water surface, which is called the setup. The second component, which is parallel to the coast, generates longshore current. These currents can be very strong and have a significant importance when we're dealing with sediment transport. The waves also generate cross-shore currents. We can distinguish the currents that are directed towards the shore and the currents that are directed towards offshore areas. The Stokes drift is directed towards the shore, and it's basically it represents the mean velocity of a fluid particle over a wave period. There is also the streaming in the wave boundary layer that is directed towards the shore. The wave boundary layer is a thin layer close to the bed where velocities goes from zero at the bed to the outer flow wave induced velocity. And the non-uniformity of the wave boundary layer generates a mean current, which is directed in the wave propagation direction. And finally, in the braking zone, there is also the mass transport, which is due to braking wave rollers. These onshore directed currents are balanced by offshore directed current, which is known as undertow. And this undertow can be very strong in the braking zone. And finally, there are also currents that are due to the non-uniformity of the bathymetry. For instance, rip currents, which are due to discontinuity in the bar. When the waves are breaking, they generate wave setup. We've seen that before, and this increases the water level inshore of the bar. Wave breaking is less intensive in the rip channels due to the larger depths, and this leads to a lower water level at this area. So due to this difference in water level, there is an offshore directed flow which is driven out through the channels. This causes very often accidents due to this. It's very dangerous for swimmers, for instance, and it's important to be very careful when there is such a system along the coast. So here is an example of a simulated wave field and its associated wave-driven currents field. And what we can see here is that the bathymetry is non-uniform, and this has an influence on the wave patterns. For instance, here in the red circle, there is focusing of the wave energy due to a shallow area, and this has an effect on the wave-driven currents, where we can see that there is an increased current. Another interesting feature we can see on this figure is the interaction between the coastal structures and the currents. And we can see that on the left part of this map that the two structures that are located along the coast have an influence on the currents. And for instance, it will generate very strong eddies or direct the currents toward the offshore areas. So now we have waves, we have currents. Let's have a look at the basic concepts of sediment transport. Here is a quick animation of how the sediments are mobilized by waves and currents over a wave period. And we will have a look at how we can calculate the sediment transport rates. In the coastal zone, we usually deal with sand, which is typically defined by grain size that are larger than 0.065 millimeters and smaller than 2 millimeters. We usually deal with sands because the finer grains are very often washed away by the waves and deposit in the more offshore and calm areas. And waves also have an impact on the larger sediments such as gravel and shingles, which can be pushed on the beach during storms. As we can see on the illustration, the sand can have different aspects, and that's why we very often have to deal with a non-uniform sand. And in order to describe a non-uniform sand, we need to have characteristics of the sand we are working with. One of the important characteristics is a grain size distribution. Here you can see an example of a grain distribution curve. Distribution is typically determined by a sieve analysis, which provides a frequency curve. So depending on the size of the sieve, we can have a certain percentage of the sand that is lower. And this provides important parameters for the sand, such as median grain diameter and the geometric standard deviation. Fall velocity is another very important parameter, which is the terminal velocity that is reached when the grain is settling in the water. And this fall velocity is dependent on several parameters, such as the grain size or the shape of the grain itself, for instance. So let's have a look at how waves and currents generate sediment transport. We typically distinguish different types of transport. The bedload transport, which is when the sediments are transported along the bed. So the grains have a more or less continuous contact with the bed. And this is mostly related to the bed shear stress. Then there is a suspended load transport, which is when the sediments are transported in the water column. Basically, this happens when the waves stir up the sediment and the longshore current transports the sediment. This is more a result of the agitation of the fluid turbulence. And then the total sediment transport, which is a sum of these two contributions. We will look at the longshore sediment transport, which is parallel to the shore, and the cross-shore sediment transport, which is perpendicular to the shoreline. These two components of sediment transport have different characteristics. The longshore transport is typically what determines changes to coastal morphology on the long term. We're talking about years or decades. It also varies on a shorter term due to season or year-to-year variations. On the other hand, the cross-shore transport is typically important for changes to the coastal morphology which occur on a short scale. This is particularly relevant for storms and cyclones and single events, but also seasons, for instance, in location where we have a strong change from season to season. So how do we calculate the longshore sediment transport rates? There are relatively simple formulas for calculating the longshore transport. One of the most known formula is the CERC formulation. This formula relates the wave energy flux at the point of breaking with the littoral drift. It's based on the idea that the littoral drift is mainly driven by the wave-driven currents and not by tide or ocean currents. It's important to note that in this formula, neither the coastal profile nor the sediment size enters the formula, for instance. But still, it's able to provide a good estimate of the longshore transport within an order of magnitude. Another way of calculating the longshore sediment transport is the use of numerical model. To use this numerical model, we typically define a coastal profile. So the bathymetry, the roughness, the grain size. Then we transform the waves from near shore over the bathymetry. Based on these waves transformation, we can calculate the wave-driven currents, and based on these wave-driven currents, we can calculate the sediment transport. This can be done for any combination of wave parameter and water level, which is very useful when we are looking at time series. So let's have a look at a concrete example of longshore sediment transport. The longshore sediment transport is heavily dependent on the direction of the waves. Here we have an example of a coast which is exposed to different types of waves, as it's indicated on the wave rows you can see. And depending on the waves that are arriving to the coast, we will have transport which will be oriented towards north because of the waves coming from southeast, and towards south, and transport towards south because of the waves from the most northern direction. As it's indicated by the arrows, we have a larger transport towards the north than towards the south. And this leads to the notion of net sediment transport, which is basically the sum of these two contributions. So here on this example, we can tell that the net sediment transport is oriented toward north because we have slightly more transport towards north than towards south. That means that in average, the sand in this area is moving or drifting towards north. This is very important when we are looking at coastline developments, as we are going to see later. Another important notion is the gross sediment transport, which doesn't take into consideration the direction of the transport, but is simply the absolute sum of the two contributions. It is an estimation of the total transport that occurs at a specific location. There are some locations where the net sediment transport is very close to zero, but with very high gross transport. The gross sediment transport is very important when we're facing problems such as backfilling of the navigation channels or the siltation in the harbors. What we define as the equilibrium orientation is the beach orientation for which the annual net transport is zero. So when working on a coastal project, we like to define what we call the Q alpha curve. The Q alpha curve is a key element for understanding the coastal processes at a site. It indicates how far we are from the equilibrium orientation, and it can also be used in order to assess the impact of coastal structure, or even estimate the lifetime of a nourishment, for instance, when protecting the coast. And this is an essential part of coastal morphological studies. Let's now have a quick look at the cross-shore sediment transport. The cross-shore sediment transport is important as a coastal profile is formed by erosion and deposition associated with a shore normal transport. And the profile is needed for the longshore sediment transport, as we've seen before. So here is a summary of the different contribution we can find outside the breaking zone. So as we've seen for the currents, we have a streaming in the wave boundary layer, which will have a small contribution to the onshore transport. Then there is also a contribution towards the shore due to nonlinear wave. So as the waves are approaching the shoreline, but before breaking, they become increasingly nonlinear, causing a net sediment transport in the direction of propagation. As we are outside the breaking zone, the sediments are not suspended high enough to get caught by the return flow. So this contribution usually lead to a small sediment transport towards the shore. When we get into the breaking zone, we have a very strong energy dissipation and turbulences due to the wave breaking. All the mechanisms that we've seen outside the zone are also relevant inside the surf zone, but their significance is small because the energy dissipation in the wave boundary layer is much smaller than the energy dissipation due to breaking. And as the suspended sediment profile is different due to breaking, we have different contributions for the sand transport. So in the breaking zone, we can say that typically usually the return flow or the undertow dominates. And as sediments are brought higher in suspension because of the turbulences due to breaking, the sediment have a tendency to be transported towards the offshore part of the profile. So in the end, the undertow will be responsible for the formation of longshore breaker bars. And this is what we can see on this animation. So this is an animation of a cross-shore profile where we have waves first subject to shoaling and then breaking. And we can see that the coastal profile is developing and that we have contributions in both directions. So the undertow gives an offshore directed transport in the surf zone, and outside the surf zone, the transport is weak with a tendency to the onshore direction. So that was the main principles of sediment transport, both longshore sediment transport and cross-shore sediment transport. So now let's have a look on how this is affected by the human projects and developments. There are different types of projects that are leading to morphological impact on the coast. The coastal structures such as ports, reclamation areas, tidal inlet, jetties can have a significant impact. Offshore structures, even though they are not located on the coast, but if they are relatively close to the littoral zone, can have an impact on the coast. And this is the case, for instance, for breakwater or wind farms or wind power plants or bridge, for instance. Sand mining and dumping of dredge material can have a significant impact on the coast as well. And finally, the last one we're going to look at today is interventions in river, such as sand mining or deepening of navigation channels or the construction of dams. And we will see how this can have an impact on the shoreline. So the coastal structure will typically block the natural transport of sand along the coast. And this will have an impact on the adjacent shorelines. So upstream we'll have accumulation and downstream we will have erosion. If the coast is long and straight, accretion and erosion will continue until the sediment can pass the structure, which may lead to a potential need for maintenance of the navigation channel. And typically another problem that can be related to the harbors, for instance, is siltation in the basin. So that's why it's important to try to optimize the harbor layouts in order to avoid problems in the harbor and around the harbor. Offshore developments can have an impact on the coast as well. But this impact is indirect, so to speak, because it's usually due to the change of offshore conditions. So as we can see here, this offshore wind farm in the bottom left corner is has a sheltering effect for the waves, which can potentially affect the wave conditions at the neighboring island. As we can see in the top right corner, the offshore development and all these artificial islands have an impact on the coast as well. So we can see here that there are some arrows. The red arrows show the equilibrium orientation of the coast before the construction of the development, and the red arrows shows the equilibrium orientation after the construction of the development. So we can see here that due to the construction, we have a significant change in the equilibrium orientation of the coast, and that due to this development, the shoreline will respond accordingly. Finally, the offshore sand mining or dumping of sediment can have an impact as well, because it affects directly the bathymetry. And as a consequence, this can have an impact on an influence on the forcing, currents and waves in the shore, close to the shore, in the coastal zone. It can be surprising, but river interventions can also have an impact on the shore. This is mostly due to the fact that these interventions have an influence on the sand supply to the coast. So, for instance, when the sun mining occurs in the river, we reduce the amount of sediment that are flowing towards the coast, and therefore the neighboring coasts that were used to be supplied by sediment can suddenly start to lack sediment, and this can potentially cause significant erosion. The changes in river flow due to dams or deepening of navigation channel or river regulation can have a significant impact on the coast as well. The reduction in the flow speed, for instance, can have an impact on the delta formation and the delta stability, which can potentially lead to the fact that the river outlets is retreated and therefore not able to supply in sediment the coast. Shoreline protection against erosion can also have a significant impact on the coast. Sometimes it's on purpose, sometimes it's not. But for instance, here we have a house that is located on very close to the shore, where significant erosion is occurring. And there has been a revetment constructed in order to block or to reduce the erosion of this stretch of coast. As the revetment blocks part of the coastal profile, it reduces erosion at the implementation location. But the problem is that the stretch of coast, which is located just north of this area, is now lacking sediment. So, as we can see on these three pictures, there is a very, very quick erosion and retreat of the shoreline that is happening. So that's why it's important to be careful when choosing a shoreline protection, because it can also have significant effect on the neighboring coastline. But this will be the subject of the next webinar. So thank you for your attention, and the next webinar will be held on the 9th of August, and it will be about shoreline protection against erosion. If you have questions on this webinar, on today's webinar, please let me know. Thank you very much.